Strawberry fields forever. Welcome to The Big Puzzle. In this podcast, we explore the subtle connections between science, religion, politics, economics, and history. One piece at a time, we unveil the big picture of this shared experience that we call life. Well, welcome to the Provo Cemetery. One thing that I like about the cemetery is that some people in their tombstones they put seats, so you can just relax, rest in peace, at least temporarily. So in this case, I want to thank the MacArthurs for providing the seating and the setting for this video. At some point, I want to talk about some of the pieces that we left dangling there, and some of those pieces are DNA, evolution, attractors, simulation, the false dichotomy between science and faith, and I think there's a few others. But to be able to connect all of those, we're still missing a significant piece, and we're going to be talking about that one today. And that's the idea of fields. I mentioned in the past how physicists in particular, they tend to use words in a completely different way than the rest of humans do. And sometimes those words are grandiloquent, but sometimes could be misleading. And I think this is one of those cases. We're going to be talking about fields. You know, when we talk about fields, we usually think about crops, or land. But in this case, we're talking fields in the physics sense means something completely different. So how can we explain what a field is? Well, a field is basically numbers in space. So imagine that around me there's a lot of numbers floating around. And that will give you an idea what a field for physicists and by extension to mathematicians mean. So let's explain a little better. What do we mean by numbers in space? First, let's simplify a little the problem. So instead of talking about multiple dimensions, 3 dimensions, or whatever, let's just talk about 2 dimensions. So let's think about a plane. Right? A plane, and in the plane we have those numbers. So each point in the plane has a number. One way we could apply that could be to terrain. So I don't know if you can see the mountains behind me, but if we think about, a big surface, a big plane all around me, you could say that those numbers could represent the elevation. So depending on where I am, the elevation has a different value. So if I could put all those numbers, in that plane, so if I'm in the mountain, the numbers will be higher. If I'm here or lower, depending on how I move, those numbers will be changing. But every point in that plane will have a value because every point has one elevation. So that would be kind of a way to explain a 2D field, right? But usually we talk about 3D. So in space, what is something that could have different values in space? So one potential simple explanation or example could be temperature. So every point in space has a different temperature. Maybe here, at this point, the temperature is, 80 degrees Fahrenheit. And then here will be 81. And here will be 79 or whatever, right? So every point in space has a different value of temperature. So we could talk about a field of temperatures where every point in space has its own value, its own number. But it's not necessarily one number. We could have several numbers in the same place. And One example that we could use is wind, right? So now the wind is different in every point. And what are the numbers that would define the wind? Well, we would need probably 4 numbers. So the first number is for this point is what is the intensity, so how strong the wind is, right? And the other 3 could be the 3 dimensions, the 3 directions in the 3 dimensions that compose the direction of the wind. So I have intensity, but I also have a direction. And to determine a direction, I have to have at least 3 different values, right? That would tell me, okay, it's this much in this direction, this much in this direction, and this much in this direction. With those 3, I can compose one direction. So a wind field will have 4 numbers in each point in space. Right? So, but you immediately could think, well, but wind and temperature are not always the same. So a few minutes ago, I was talking about this point, probably here, and I said, 80 degrees, and now it's probably 81 or 82 or 78. So fields sometimes, or most of the time, are mostly useful in at least 4 dimensions. So the 3 physical dimensions plus time, because things change with time. Even terrain, we could say, well, terrain changes very, very slowly, unless you have a big earthquake, but still, it's changing, right? So those are the 4 dimensions. And, physicists could come up with examples where they need 10 dimensions or whatever. We already talked about that. But let's try to keep it something that we can understand. Now, both wind and temperature and we could talk pressure or any other of those things are actually connected to some particle. So we don't have temperature in the vacuum. When I said that the temperature here is 80 degrees, I'm probably grabbing one atom that is vibrating according to the temperature. So the energy of that atom is related to the temperature. But if I could remove that atom, so I wouldn't have a value of temperature just in the vacuum. Same thing with with wind. So we're talking about the speed of molecules of air, right? Molecules of air, yeah. Any of the components of air, right? But again, it's connected really not to the point in space, but whatever is at that point at that time. And well, truly, the most of the space is empty because the nucleus is so small, and electrons are so far away, and so. But we can talk about it some other time. But really, those examples that we put are connected to something that exists physically. But is there anything that actually has a value, even if there's nothing there? And surprisingly, yes. And those are the most baffling things in physics. And the first one that we can think of is gravity. So around any object that has mass, we have a field of gravity, and the attraction to that object grows as you come closer to the object and points towards the center of gravity of that object, right? But it decreases when you go farther and farther away. Even if there's no atoms, even in the vacuum, when there's nothing there, you still have a value for the attraction of gravity from that object at that point in space. Which is weird. Well, Einstein explained it by, well, it's not really, a field, it's just a distortion of the space produced by that mass. Yeah, and that explains that could explain mathematically what you're seeing, but from our human perception, what we're seeing is, there's some force pointing in this direction and has certain intensity. And that has to do, and again, I say force, and you say, well, it's not really force, well, some acceleration, if you will. There's other two that also come to mind, and the first one is magnetic force. So again, if I have an object that is, magnetic, you have a field, a magnetic field around that. Even if there's nothing, it's not in the molecules, it's not anywhere, it's just a value, and has a direction that goes from north to south, right? So from the object. And that, again, doesn't require to have any medium, any element. It's just a property of the space around that object. But that can influence other objects. Another magnetic object could be, it generates a force between them two. The other one is similar, is electric fields. And those are produced by electric charges. Now, when we talk about the fourth dimension, that is time, those two become indivisible, become part of the same thing. Let me explain. When a magnetic field changes in time, at a certain point, that produces an electric field. And when an electric field changes in magnitude through time, it creates a magnetic field. So now the two of them together, they affect each other and they're interconnected. You can only have a single magnetic field if it doesn't change with time. And you can also have only a electric field if it doesn't change with time. As long as they change, and that could be by the object moving or whatever, right? So they start producing each other. And in many cases, that produces an oscillation. So one follows the other. And that's what we call electromagnetism. And basically light and everything, that radiates is electromagnetic. So X-rays, infrared, and all of that radiates, and it doesn't require a medium. So we receive electromagnetic radiation from the sun, even though it's mostly empty, mostly vacuum between the Earth and the sun, but still those rays come here, and the rays are just the propagation or the vibration of those fields, right? So the vibration of the field produces changes in the rest of the field, and that's what we call radiation. Okay, so where are we going with all of this? To be able to connect other pieces, we need to explore this a little more, because I need to introduce another concept that I think is very, very important. That is actually the part that connects with the other pieces in this puzzle. So let's go back to the temperature. So I have my point in space here with a certain value, 80 degrees. We have three possibilities. Now we're going to look around, everything around, so a little sphere around that point that I picked. It could be that that's a maximum, that everything around that point has a lower temperature than that point. Or it could be that it's a minimum, a local minimum, so that everything around that point is greater, has greater temperature. But those are very unusual, right? So you don't find those all over the places. So what you usually find is that from one side, and we're going to define side of what, from one side the temperature is lower, and from the other side the temperature is higher. Which means, and this is mathematical and maybe might be shocking to if you think about it, but if you think a little more, it makes complete sense. It means that there's a lot of other points around that point that have the same temperature. And they produce a plane that has the same temperature. And that plane could extend, and it's not flat necessarily. It could be, moving around, but it's basically a two-dimensional surface of all the points that have 80 degrees. And then if we move a little, we have another surface that has all the points that have 79 degrees. And then we move it and 78. And on the other side, we have 81, 82, 83. So you can think it as, onion layers, in which each layer has all the points in space that have the same value. So if it's still hard for you to understand, we can go back to the 2D example. Right? So if you're in a terrain anywhere that you are, it's not likely that you are in the highest point, right, on the top of the mountain. It's not probably that you're in the lowest point on a valley. It's likely that you're somewhere, anywhere. So that means that you can always find points around you, elevations around you that are the same elevation that you are. And we call those contours. So they are equal elevation. And you can walk through those contours, right? And you never change elevation. You just have to follow, the points in the terrain that have the same elevation. So that is the same concept. Now you take it to 3D, and now for every field, you have those surfaces, that actually are contours. Have the same value, and they're continuous most of the time. There could be discontinuities, depending on what kind of field and other things. But in a terrain you can have a cliff, so the elevation suddenly drops. But the same thing could happen with other things. But in general, those are more or less continuous. Right, so you can always go from one point to another that has the same value. And yeah, you have those peculiar points that are high points, high temperature, the maximum temperature, and the minimum temperature. Again, think about the terrain. If you're at a high point, all the contours below you kind of create circles or curves, close curves around it. So in a map, you can look and say, okay, if you want to find where is the highest point, you just look where all those circles or close curves, get into one point, and that is the highest point, or the lowest point looks the same, right? So you have all the contours that kind of close up to the lowest point. In 3D, those high points actually are kind of spheres. I mean, not really spheres, but you get the idea. So a closed surface. So if I have my highest temperature here is 90 degrees, and that is the highest. So the 89 would form, a little blob around that, and the 88 and the 87 and so on. So, okay, so that is something that is interesting to think about, and it connects to the next thing that again it's not intuitive, I think, until you think a lot about it. What if you want to gain or lose elevation as fast as possible? That would mean, where is the maximum slope? How do I move faster, up or down? And mathematically, you can prove that is orthogonal or 90 degrees from the contour. So if my contour goes like this, if I go 90 degrees, I'm guaranteed to go the lowest and the highest. Right? It's not 45 degrees, it's always 90 degrees from the contour. And the same thing happens in space. If you have this blob of equal temperature, if you move perpendicular, orthogonal to the surface of that blob, you would increase or decrease temperature the faster. And that's what we call, in mathematics, the gradient, right? The maximum gradient, the maximum slope. And that idea of gradient is the one that actually will connect everything together, hopefully, in a future video. But there's something more, and then I promise I will stop this one. I talk about electric fields and magnetic fields, and how they are interconnected. But pretty much everything is interconnected with everything else. Surprise, the big puzzle. But let's talk about temperature. We talk temperature, we talk wind, I mentioned pressure, electromagnetism, radiation from the sun. The radiation of the sun, that field, affects the temperature because it makes vibrate the molecules that are impacted by that energy, and the more they vibrate, the more temperature they get. And then you have pressure, because those that are vibrating try to separate from others. There's no room for all of them to vibrate together. So that's why when you have more temperature, you have lower pressure, right? If it's not contained, if not, you have more pressure, right? But you allow the particles to move away from each other, so you have less particles in the same. So yeah, I misspoke. It's not changing the pressure, is changing the density, because you have less particles in the same volume, right? Because they have to move apart. But also that change in density is affected by gravity. So things that are more dense tend to be attracted more because they have more mass, and the gravity field from the Earth and from those particles, make them move with greatest force towards the Earth. And the lighter, the less dense air moves up. So now you have the whole surface of the planet with different radiation from the sun because the Earth is rotating, and then you have the temperatures changing, and the pressure changes, and the density changes, and now the air has to move from one side to the other because it tries to get to the same level, right? The same energy. So now you have winds. So as you can see, all the fields at the end up being affecting each other, and I think that's so great. But now we're talking about inanimate objects, right? Things that they don't have a wheel, and they don't have they don't make decisions. What happens if we put that into the mix? What happens if we add some quantum physics into this? Right? Because now I was talking, this particle, that particle, but now we go to quantum physics and say, we really can't tell where the particles are. We can't tell how they're moving because of the uncertainty principle. The more we know about, the more precise we know about their position, the less we know about their velocity or momentum. And on the contrary, the more we know about their momentum, the less we know about what they are. So everything becomes a probabilistic thing. Making everything more complicated, but also way, way more interesting. So, okay, I think that we talk about a lot, these things. So I hope that you learned something, and if you didn't, at least that you can see them under a different light. And yeah, if you want to review some of the previous videos, I really hope that soon I will be covering and connecting all these other pieces. And really, I think that we're starting to see the hand of God, right? And I don't know, just a teaser. I think that the big puzzle is basically going to, once we put it together, we're going to be finding God there. But we're not there yet. I'm not there yet. I mean, I wish I were. So this is kind of my way to think aloud, hopefully to get some feedback from you guys, and yeah, learn together and figure out together how to put together the pieces of the big puzzle. So with that, hope to see you in the next one, and bye.